Good evening, everyone.
Good evening, Neet.
So, last class we have been discussing organic chemistry. So, in which we have discussed aromaticity, right? Do you remember? What are all the conditions to be followed by an organic compound to be aromatic? We have seen 4 conditions, right? Do you
Yes, ma'am.
remember? What are all the conditions to be followed by an organic compound to be an aromatic compound?
Cyclic,
Very good. Cyclic.
linear molecule,
Very good.
conjugated double bond,
Superb.
Hooke's rule, ma'am.
Brilliant. What is Huckel's rule? What is Huckel's rule? What is that rule? If an organic compound contains 4n plus 2 pi electrons, then that compound is following Huckel's rule. Okay. What is so special about organic compound? What is so special about aromatic compound? So basically, aromatic compounds are usually a very stable one, right?
Yes,
Okay. Aromatic, non-aromatic, anti-aromatic. Could you please arrange these compounds based on their stability? Anti-aromatic, non-aromatic, aromatic. Yes, Mushkin?
aromatic high stability, ma'am.
Very good.
Anti-aromatic high unstable.
Superb, Kana. Superb. So, have to find whether the compound is planar. Planarity is one of the conditions, right? So, how?
Plus cation and anion, ma'am.
Okay. The first point is we have to check all the compounds are sp2 hybridized carbon. If it is not sp2 hybridized, but if we got any positive or negative charge, then we can consider that as a planar one. Okay, fine. That's it. So today we'll start with organic reaction. What are all the terms we are using in organic reactions, different types of organic reactions, and reaction mechanism. Okay, fine. So we'll start with organic reaction. Shall we?
Okay, ma'am.
Right. So generally in a chemical reaction, the species getting involved in the chemical reactions are called reactants, right? And all the reactants will get involved in a reaction to give a new compound, which is product, right, Kana? So here also we'll be using a few terms like that, but generally we'll be calling it as reactants, right? The species which is getting involved in a chemical reactions are called reactants, but in organic chemistry, we are not going to use the term reactants. Instead, we're going to use the term substrate and reagent. Substrate and reagent will get involved in a chemical reaction to give product. Basically, substrates are the organic compound on which chemical reaction will occur. Definitely, substrate will be an organic compound. On this organic compound, chemical reaction will occur. And reagent is the chemical species which is responsible for the chemical reaction. Okay. And reagent can be either organic or inorganic. Substrate and reagent will get involved in a chemical reaction to give a new compound called product. That's it. So I'm going to write a chemical reaction and I want you guys to tell me which is substrate, which is reagent. Guys, could you please tell me which is substrate, which is reagent, and the product?
Propene on organic compound. Propene substrate, ma'am.
Gana, which is substrate?
Ethene, ma'am.
Ethene. Okay, okay, right.
Reagent on hydrogen, ma'am.
Hmm. So ethane is product. Okay. So basically, this is an organic reaction, and here instead of this double bond, two hydrogens were added. So this is my organic reaction on which chemical reaction took place. So this is my substrate, and this is my reagent. That's it. And in reagent, we have a very famous two types. There are two types of reagents. One is electrophile, and another one is nucleophile. See, basically, electrophiles are electrons loving species. They love electron. Why? Because they do not have any electron, so they are in need of electron. So they are basically electron deficient species. So electron deficient species are called electrophiles. So this is electrophile. Whenever I'm talking about electrophile, please visualize it as E plus, because generally positive charge represents electron deficient one, right? Similarly, nucleophiles are just the opposite one. Nucleophiles are electron rich. Basically, nucleophiles are electron rich species, so they may be a negatively charged one, or they may be a neutral molecule, but they'll be having a lone pair of electron. That is why we are considering that as electron rich system. And electrophiles, as I've told you already, they are electron deficient systems. And electron deficient system, they can be a positively charged one, or it can be a neutral molecule, but they shouldn't have a perfect 8 electrons in the outermost shell. For example, BF3, boron trifluoride, seems to be a neutral molecule, but in this BF3, boron is your central atom, and this boron is connected with 3 fluorine atoms, right? So boron got 3 covalent bonds, and each covalent bond got 2 electrons. So around this boron, we have only 6 electrons, and basically we know that in a molecule, central atom should have 8 electrons to complete its octet, right? But here boron got only 6 electrons, so it is in need of 2 more electrons. So though this molecule seems to be a neutral one, it is in need of electron. So this is also considered to be an electrophile. So basically, electrophiles are positively charged species, or the compound with incomplete octet. Sometimes the compound with d block elements also considered to be an electrophile. Basically, d block elements usually will have a vacant orbitals to accommodate incoming electron. So d block element containing elements were, d block element containing compounds were also considered to be an electrophile. Okay, fine. So these are all the conditions for being electrophile and nucleophile. Fine. That's it, Kana. These are all the terms we're going to use in any organic reaction. Now we're going to get into the different types of organic reactions. Basically, we have 3 types. Addition reaction. The first one is addition reaction. See, addition reaction is a very easy reaction. See, it is basically very simple. In a substrate, if the reagent species were added, just added to give a new compound, then that is an addition reaction. See, here I've already wrote the reaction. CH2 double bond CH2. This is my substrate. And this is my reagent. So this was the product, right? Listen here. In my substrate, there are 2 carbons and 4 hydrogens. And reagent, there are 2 hydrogens, right? in my product, these two hydrogens were added to the substrate. So basically, the reagent were just added to the substrate to give a new compound. So this kind of reaction is called addition reaction. Reagent is just added to the substrate. Okay, but the very important point is in all the substrate reaction or addition reaction will not occur. Substrate definitely should have at least one double bond or triple bond. So basically, the substrate has to be an unsaturated compound. Then only addition reaction will occur. Because in a double bond, we know we have pi bond and single bond. I mean sigma bond. Among sigma and pi, which is considered to be the strong and which is considered to be the weak? Among sigma and pi bond, which is stronger one and which is weaker one?
Pi is weaker, ma'am.
Yes. So here in my substrate, here I got this pi bond, right? This pi bond was broken. Instead of this pi bond, two hydrogens were added to the substrate. So for addition reaction to occur, the substrate definitely should have either double bond or triple bond. Then only we'll be having pi bonds for getting involved in the reaction. And whenever we have pi bond in my substrate, this pi, which means the double bond in my substrate, the double bond will get converted into single bond. See here, that is what happened. That is what happening, right? Initially, it was double bond. Now, after addition reaction, it got converted into single bond. Similarly, in a triple bond, if addition reaction occurs, it will get converted into double bond. That's it. One of the pi bonds will get, instead of one pi bond, hydrogen or any reagent will get added. That's it. So this is addition reaction. Second one is elimination reaction. It is just the opposite of addition reaction, Kana. Could you please tell me what is elimination reaction? As I told you already, it is just the opposite of addition reaction. So what will happen in elimination reaction?
The compound breaks into two compound, ma'am.
Not exactly. If the compound is broken into a smaller one, then that is called a decomposition reaction. Elimination reaction is in a substrate. We know substrate is an organic compound, and we know organic compound is usually a larger one, right? In that substrate, any atom or any group will get eliminated. And for that elimination to occur, reagent will be helpful. That's it. So basically, compound will not break. Any atom or any group of atoms will get eliminated. That's it. And I'll give you an example. It is very a basic example. And as far as elimination reaction is concerned, we're going to discuss this elimination reaction in our 12th standard syllabus also, where we'll be seeing mechanisms also. So here I'm just writing the plain example. CH3, CH, single bond CH3. And here I have a functional group. Could you please tell me what functional group was that?
Bromo, ma'am.
Yes, very good. Could you please tell me how many alpha hydrogen and how many beta hydrogens were there? How many alpha and how many beta hydrogens were there?
1 and 6, ma'am.
Very good, Kana. See, Sendamil Shelvan was right. The carbon which is directly attached with the functional group is considered to be alpha carbon, and the carbons which are directly attached to this alpha carbons are called beta carbons. Hydrogens which are attached to alpha carbons are called alpha hydrogens, and hydrogens which are attached with beta carbons are called beta hydrogens. So this is my alpha carbon. So this is my alpha hydrogen. These are my beta carbons and these are my beta hydrogens. That's it. So here I'm going to write the elimination reaction. Here I have 6 beta hydrogens, in which one of the I'm just writing the I'm just writing one of the hydrogens individually. Usually it will be like this only, right? What will happen is the reagent what I'm going to use is alcoholic potassium hydroxide. Maybe the combination of methanol and potassium hydroxide, or ethanol and potassium hydroxide. Any alcohol with sodium hydroxide or potassium hydroxide. What will happen here is we have potassium hydroxide. How it will get ionized? Potassium plus and OH minus. Right, Kana? So what this OH minus will do is, this OH minus is electron rich. What this OH minus will do is, it will take this hydrogen without any chemical bond. So hydrogen will leave its chemical bond to the carbon atom, and hydrogen will be removed as H plus, and H plus will be taken away by OH minus. So this H plus and OH minus will get converted into water. Here what will happen? I have one chemical bond here, right? It will get transferred between these two carbon atoms. Now the problem is for this carbon. Generally this carbon already got 4 chemical bonds, right? 1, 2, 3 and fourth bond is with hydrogen. Now we got a new chemical bond between these two carbon atoms, that is going to be the 5th bond, which is unstable obviously. So what bromine atom will do is, bromine will take this chemical bond and it will get removed as Br minus. So Br minus will combine with K plus to get converted into KBr. So now my product is CH2 double bond CH single bond CH3. That's it. So what are all the species which got eliminated from the substrate? What are all the species which were eliminated from the substrate?
1 alpha hydrogen and bromine, ma'am.
Bromide is right. What hydrogen was that, Sindhamir Chelvan?
Beta hydrogen, ma'am.
Yes, one beta hydrogen and bromine were eliminated. See, I've removed one beta hydrogen from left side carbon. We can also remove hydrogen from right side beta hydrogen also. For example, if I remove a hydrogen from this carbon, then what will happen? The product will be CH3, CH double bond CH2. Could you please name these two compounds, Kanna? Have to name an organic compound. We didn't discuss that, but I believe you will be having a basic idea for naming. Come again, Sandhamir Chelvan.
Propene?
Yes, it is. See, whenever an organic compound is given, you have to find what is chain and what all the branches we have. As far as this compound is concerned, we have no branch there. We have only one chain. So this is my chain. After finding which is the chain, we have to start numbering it. We can number the compound from left to right or right to left. I'm going to number in both the way. 1, 2, 3. I'm just numbering the carbon atom. From right to left, it is going to be 1, 2, 3. Now we have to decide which is right. Kanna, whenever we are numbering, we have double bond in the organic compound, right? Double bond should have least locant. Locant is nothing but the number what I'm writing there. So double bond should have least locant. As far as the numbering, what I've done from left to right, double bond was between first and second carbon. In second numbering system, the double bond was between second and third carbon. Which is right? This one is right. Okay, because double bond is between first and second carbon and double bond should be at the least locant. So totally I have 3 carbons. So it is prop. And obviously we have double bond. So it is ene. Double bond is between first and second carbon. So this is prop 1 ene. That's it. Here also I'm going to name the compound. See, here also we have no branch. This is my only chain. And how should I number this here? Here, how should I number? This is 1, 2, 3. In this numbering, double bond is between second and third carbon. 1, 2, 3. Here, the double bond is between first and second carbon. Now, which is right? Which numbering is right?
Second, ma'am.
Yes. So from right to left is right. And I have 3 carbons in my chain. So prop, and double bond is between first and second carbon again. So this is also prop-1ene. So here, as far as this organic compound is concerned, this substrate is concerned, if I remove this hydrogen or this hydrogen, we are getting same product. But it is not same for all the elimination reaction. It will vary, but we'll discuss that in depth in 12th standard. Now you just understand what is elimination reaction. In my substrate, hydrogen and bromine were eliminated. After elimination, the place where we had a single bond, now it got converted into double bond. That's it. Okay, fine. Any doubt? Any doubt? Mushkan? Shall we proceed?
Okay, ma'am.
Right. This is elimination reaction. And third reaction is substitution reaction. What is meant by substitution reaction?
One element is substituted, ma'am.
Right. In my substrate, one group will be substituted. For example, say I'm going to write a chemical reaction. This is my substrate. And this is my reagent. Okay. What is going to happen is, say instead of Br minus, OH minus from sodium hydroxide will get attached. So this is what the substitution reaction is. In my substrate, one of the groups will be replaced with one group from the reagent. That's it, Karna. So this is substitution reaction. And as far as substitution reaction is concerned, we have 2 types of substitution reactions. One is nucleophilic substitution reaction. Another one is electrophilic substitution reaction. Nucleophilic substitution reaction is nothing but, basically what is nucleophile? Is it electron rich or electron deficient?
Electron rich, ma'am.
Yes. So from my substrate, any electron rich group will be replaced with any electron rich group from the reagent. That is nucleophilic substitution reaction. Similarly, from my substrate, any electron deficient group will be replaced by any electron deficient group from this reagent. That is electrophilic substitution reaction. And as far as nucleophilic substitution reaction is concerned, we have 2 mechanisms. A very famous one. If you guys are from 12th standard, definitely you would have heard these 2 mechanisms, SN1 and SN2. Substitution nucleophilic unimolecular, substitution nucleophilic bimolecular. So this is a very famous 2 mechanisms. That's it. So these are all very important very important organic reactions, Kanna. That's it. So we saw what is organic reaction, different terms we have been using in organic reactions, and different types of organic reaction. That's it. Next, we're going to see reaction mechanism, or it is also called as reaction pathway. Shall we proceed?
Okay, ma'am.
Right. Generally, in an inorganic reaction, we will not consider this mechanism at all. We'll be studying these reactants are getting converted into this product. That's it. We will not worry about how this reactant got converted into product. But in organic reaction, in organic chemistry, we'll be studying how these chemical reactions are happening, how these bonds are getting broken, and how new bonds are getting formed. We'll be highly concentrating on the way in which chemical reaction is happening, and that is called reaction mechanism. And whenever any question is from the organic reaction, definitely for most of the reactions, we have to know the background mechanism to find the product. Okay, and as I've told you already, see here I've written as far as elimination reaction here I've written is concerned, I have two products, but both the products are same. But in usual organic reactions, we may get two different products. Whenever we have two different products, definitely one product only will be major, so another product will be getting in a minor quantity only, and a question may be asked to find which will be the major one. So to find which product is major, we have to have the knowledge of this reaction mechanism, then only we can find which product is major. So understanding the reaction mechanism is very important, Kana. At least we have to study the mechanisms which are in your syllabus. Yeah, for a few reactions they'll give you the mechanism, for a few reactions they'll not give the mechanism. If they didn't give you the mechanism, no issues, you don't worry about it. But whenever the reaction mechanisms are given, please understand the mechanism. Please don't memorize it, please understand the mechanism. Only then you can always predict the product. Just by memorizing, it is no use, Kana. That too, in any entrance exam is concerned, memorizing the mechanism will not work. Fine. So the first mechanism, say I'm just giving you the very important the way in which reaction will occur. Whenever we are discussing the specific chapters, we'll be discussing all the reactions particularly. Okay, so the first pathway, mechanism number 1. I'm going to give you a hypothetical chemical reaction. AB plus CD, these two reactants are getting converted into AC and BD. Kana, this is a very hypothetical one. Listen here. Actually, what happened in this chemical reaction is I didn't start the mechanism yet. This is my general chemical reaction where AB was connected initially and CD were connected initially through a chemical bond. But in a product, A and C got new chemical bond, B and D got new chemical bond, right? So this is basically a chemical reaction. Old bond will get broken and new bond will get formed. So this is chemical reaction. And the mechanism is we're going to understand how these chemical bonds are broken and how these chemical bonds are formed. So that is basically a chemical mechanism. So here, whenever we are using any light energy for the reaction, or whenever we are using any peroxides as our one of the reagents, then we have to understand how these chemical bonds are broken. See, whenever we are using light energy for the reaction, then that kind of chemical reaction is called photochemical reaction. So whenever we are using light energy, the substrate's bond will get cleaved homolytically, a proper bond cleavage. So here one electron will get transferred to this atom and one electron will get transferred to this atom. See, only one electron is getting transferred to each atom. That is why I've represented it using single header arrow. So similarly, between C and D, we have a chemical bond. Upon proper homolytic cleavage, each atom is getting one electron. So because of this homolytic cleavage, we got one electron on A, one electron on B, one electron on C, and one electron on D. Once the bonds are broken completely, now a new bond is formed between two species. See, here A got one odd electron, C got one odd electron, and here both the electrons were shared between two atoms. Now this got converted into AC product. Similarly, B got one electron, D got one electron, and both the atoms were sharing these two electrons to get converted into this product. That's it. So this is how this chemical reaction occurred. See, you may think why A and D, why A and D didn't get combined together to form AD. See, mechanism is what we are writing. Initially, I'll do the reaction. I know A, B, and C, D were my reactants. After the reaction was over, I know A, C, and B, D were the product. If this is the product, from the product, I'm just guessing the chemical reaction or reaction mechanism. Not because if I write the chemical reaction, that will not happen. Already I know this. These are my products. If these are the products, then this may be the chemical reaction. That basically the chemical reaction is what I'm assuming and I'm writing it. Okay. So here, if AC is the product, then definitely A and C would have combined together. That is what the mechanism is. So after the chemical reaction happen only, we are writing the mechanism. It is not another way around. So see, we have to understand these chemical species. Karna, they are not our substrates or they are not our starting material, reactants. And similarly, they are not our products also. Here, they are not our reactants. They are not our products also. They are called as intermediates. In organic chemistry, we have so many types of intermediates, but we're going to concentrate on 3 types of intermediates. Here, this is one of the kind. Listen here, we got one electron on an atom. Or if we got one electron on group of atom, then that intermediate is called, any guesses? Could you please name this intermediate? We have very famous 3 types of intermediates in organic chemistry. If an atom got one electron, one odd electron on the system, that is called free radical. Free radical. So in this mechanism, we got free radical as intermediate. So when we'll get this free radical as intermediate, whenever we are using light energy or whenever we are using peroxides in the reaction, or if we are using any organic solvent for the reaction, then we may end up with intermediates as free radicals. Okay. So this is mechanism number 1. We'll concentrate on next mechanism. I'm going to use same that hypothetical reaction. A, B, C, D combines together to give AC and BD. Now I'm going to use heat energy. Not the light energy, heat energy. Basically, here the reaction is thermal reaction. Or if I'm using any polar solvent, any solvent with positive and negative charge. In this case, a chemical bond between AB and AB will be broken like this, and both the electrons will get transferred to any of the atoms. It is not a proper sharing of electrons, right? Here, one electron was transferred to one atom, another electron was transferred to another atom. Here, both the electrons will transfer to any of the atom. For example, if both the electrons were transferred to atom B, then what will be the charge on B and what will be the charge on A? Here, two electrons were transferred to B atom. In two electrons, one of the electrons was B's electron itself. So B will not have charge for that. But this is an extra electron from A which got transferred to atom B. So this B atom will have a negative charge. And what happened to A? It lost its one electron, right? So A will have a positive charge. Similarly, so both electrons were transferred between atoms C and D. Upon heterolytic cleavage, maybe both electrons were transferred to C. So C will have a negative charge and D will have a positive charge. Now this positively charged A and negatively charged C formed a new chemical bond. Similarly, negatively charged D and negatively charged B and positively charged D shared a chemical bond. Now a new product is formed. See here, these are not my substrates. These are not my reactants. They are not my products as well. They are also called as intermediates. Here in this intermediates, we got positive and negative charge. Basically, this is an organic reaction. So anyways, positive charge will be on the carbon. Anyways, negative charge will also be on the carbon atom. Basically, positively charged species are called cations. Here, positive charge is on carbon atom. So this intermediate is called carbocation. Here, negative charge is on carbon atom. So it is called carbanion. So in organic chemistry, we're going to discuss these three intermediates: free radical, carbocation, and carbanion. Okay, fine. So this is mechanism number 2. And last category. In first two scenarios, what I've done, I've broken the bond completely. It can be homolytic cleavage or heterolytic cleavage, but I've broken the bond completely and I've attached two atoms together, right? But what I'm going to do here is, or actually what is happening here is, now bonds are not getting broken initially. These two molecules are coming closer. So when these atoms are coming closer, let us understand what is happening. Kana, when these two molecules are coming closer, there is a new attraction is formed between AC and a new attraction is formed between BD. So what will happen to the older one? Older bond will started breaking. So here simultaneously older bonds are getting broken and new bonds are getting formed. Okay, and immediately after this new attraction was formed, we'll end up with new compounds which are products. See, this is also a intermediate stage, right? But this is not called as an intermediate. This is called as transition state. Intermediate and transition states are two different species. Okay, intermediates are relatively stable. They can stay in a chemical reaction for fraction of seconds, but transition states are highly unstable. So, while we are discussing few mechanisms, you'll understand when we are getting transition states, when we are getting intermediates. Okay, but intermediate transition stage is also a stage before a before a chemical product is formed. Okay, that's it, Kana. So here we discussed three mechanisms. In first mechanism, because of homolytic cleavage, we end up with free radicals as intermediate. And then second mechanism, upon heterolytic cleavage, we end up with carbocation, carbanion as intermediates. And third mechanism, we got transition state. So usually while we are discussing any mechanism, anyways, we'll be encountering all these terms. Okay, you understand? Any doubt?
No, ma'am.
Fine. That's it, Kanna. As I've told you already, understanding the stability of understanding these intermediates are very important, because whenever in a chemical reaction, we may have more than one type of intermediate. And we have to understand which intermediate is stable, because only the stable intermediate will give the major product. Okay, so understanding the stability of intermediate is very, very, very important. So to understand that, we're going to discuss a few electron displacement effects, or it is also called as electronic effects. So you should have studied in your 11th standard. Could you please tell me what are all the effects I'm talking about? There are 4 electronic effects. There are 4 types of electronic effects. Definitely you would have encountered these topics in your 11th standard class. Any idea, Kanna?
Inductive effect.
Very good. You're right, Kanna. Inductive effect. Hyperconjugation. Mesomeric effect. Electromeric effect. Very good. Kavita. You are from 11th or 12th, Kavita?
12th.
12th standard. Okay, very good. CBSE or state board?
State board.
Super.
State board.
Okay, Kanna. Very good, Kanna. Very good. Okay. So we have 4 types of electronic effects: inductive, hyperconjugation, mesomeric, and electromeric effect. So first, we'll see all the effects individually. First one is inductive effect. See, inductive effect is one of the electron displacement effect. First, let us understand what is this electron displacement. Kana, basically, what is displacement? What is displacement or electron displacement?
Like substitution reaction, ma'am.
No. Okay, listen. For example, I have a covalent bond. In a covalent bond, generally, will there be any charge separation? Will there be any charge separation?
Yes,
Or what
ma'am.
is okay? What is covalent bond?
Electronegativity ஒன்னு அதிகமா இருக்கும் மேம் ஒன்னு கம்மியா.
In very special case, generally in covalent bond, 2 electrons were shared between 2 atoms. If both the atoms are same atom, then as Kavita's point, there is no electronegativity difference at all. If both are same atom. Kana, what is your good name?
சீதனா.
Tidna. Am I right, Kana?
சீதனா.
ಇದನ್ನ. Okay, right. So if the chemical bond is formed between uh, two atoms of same type, then we will not have any electronegativity difference. So two electrons were properly shared between two atoms, so there will not have any charge separation. If two atoms electronegativities are nearly same, if there is no significant difference, then also we will not have any charge separation. But if both the atoms electronegativity difference is very huge, one atom got high electronegativity, another atom got very less electronegativity, then the atom with highest electronegativity will pull the electron towards itself. It will attract the bonded electrons towards itself. Actually, the covalent electrons or the shared pair has to be at the middle, center of the two atoms. But if any of the atoms got highest electronegativity, that atom will pull the paired electrons towards itself. So, for example, electronegativity of B is greater than electronegativity of A. Then what will happen? Both the electrons, this pair will move towards this B. This is called displacement. Electron is moving from one place to another place. This is called displacement. Here, this electron is displaced towards B, so B will have a negative charge, but here electrons were not completely transferred. It is just moved towards B, right? It is not transferred completely. So B will have a partial negative charge and A will have a partial positive charge. You getting my point? So because of this displacement of electron, a charge separation was there. A charge separation was developed. So this is the essence of this electronic effect. Here, sigma electrons were moved towards B. In some cases, for example, I have atom X and atom Y, and these two bonds were connected using double bond. As we know, if we have double bond, one is sigma, another one is pi, and we know sigma bonds are weaker one. So this pi bond can get transferred to one of the atoms. So what will happen? Now X single bond Y. Now both the electrons were transferred to Y atom. So Y will have a negative charge and X will have a positive charge. Now also there was a charge separation because of complete transfer of electron. So these are all basically electron displacements. Because of electron displacement, there was a charge separation on the molecule. So how these electrons are being displaced, based on that we have 4 types of effects: inductive, hyperconjugation, mesomeric, and electronic effects. In all the effects we'll be discussing the charge separation because of the electron displacement. Okay, fine. So now we'll talk about inductive effect. See, in electronic effect, as I've told you already, we have 4 types, right? Among these 4 types, 3 types of effects were temporary effect. Because of the inbuilt structure of organic molecule, there will be a charge separation. The 4th category, which is called electromeric effect, which is a temporary one. Basically, that molecule will not have any inbuilt charge separation. But in the presence of any reagent, there will be a charge separation. And if you remove the reagent, then it will get converted into a normal neutral molecule. Okay. So that is why it is called as temporary. But rest of the effects will be a permanent one. Because of the inbuilt structure of organic molecule, there will be a charge separation. So first we'll talk about inductive effect. What is the name of this compound?
Butane.
Yes, it is butane, because we have 4 carbons and all the 4 carbons are connected through single bond, and all the carbons valencies were satisfied using hydrogen atom. So it is butane. As we know, we have carbon-carbon bond, which is non-polar. Carbon-hydrogen bond is also non-polar, so there is no charge separation here. But here, what I'm going to do is, instead of this hydrogen, I'm going to substitute a special atom or special group. If suppose this group is highly electronegative, then what it will do, it will attract the bonded pair of electrons towards itself. So basically they are called electron withdrawing group. So what this electron withdrawing group will do, it will pull or it will attract the bonded electrons towards itself. Because of that, this group, this special group will have a partial negative charge, and this carbon will have a partial positive charge. Initially, both the carbons were same carbon atom, so there is no charge separation here. They'll be properly sharing their electrons. But now this carbon got one partial positive charge, right? So it is in need of electron. Now this positively charged carbon will attract the shared pair of electrons towards itself. Though it is attracting the electron, this cannot pull the electron as strong as this group G. Still it will attract. So this carbon will have a positive charge, but it is very much lesser than the positive charge on this carbon atom. And what this carbon will do now? Now it is electron deficient. It will pull this electron towards itself, this pair of electrons towards the second carbon, and we will have a very, very little positive charge on third carbon. And this effect will not be there after 3 or 4 carbons. That's it. Now, because of substituting electronegative group in a hydrocarbon, this group is attracting the electron, because of which the sigma electrons were displaced and there was a charge separation, right? And this is called inductive effect. Because of displacement of sigma electrons, we got positive and negative charges, right, Kana? This is inductive effect. Here, if my group is electron withdrawing group, it will attract the electron, and this is called -I group. If I'm substituting any electron donating group, then it will push the electron towards the carbon chain. So that is called +I group. Kana, usually alkyl groups are +I groups, methyl, ethyl, propyl, butyl. All these alkyl groups are +I groups, and all functional groups are -I groups. Alcohol, chlorine, chlorofluoro, bromo groups, aldehyde, ketone, carboxylic acid, nitro groups, all were electron withdrawing groups. In the sense, they are -I groups. Okay. I'll give you the proper order for -I and +I. I'll show you the order. See. Here there are so many functional groups, and this is the proper order, Kana. Fluorine, chlorine, bromine, iodine. Fluorine got highest electron withdrawing property. Then chlorine, then bromine, then iodine. So you have to memorize this order. And as far as +I groups are concerned, these are all alkyl groups. But if the number of carbon atoms are increasing, then electron donating property is also increasing. That's it. While sending you the notes, I'll give you this also. That's it. So this is what the inductive effect is. Now we have to understand how this inductive effect is stabilizing our intermediates. Kana, you have to understand one point. If you take any carbon atom should have 4 chemical bonds. Carbon atom should have a proper number of electrons to be stable. If the carbon atom contains less number of electron, if the carbon is electron deficient, then that is unstable. If the carbon contains more electron also, that is unstable. Carbon should have proper number of electrons to be stable. If it is electron deficient, also unstable. If it is electron rich, also unstable. So now we'll talk about a carbocation. Could you please tell me carbocation is electron rich or electron deficient? Carbon with positive charge is electron rich or electron deficient, Kana? What this positive charge represents? Is it electron rich or electron deficient?
Electron deficient.
Yes, it is. So positively charged carbon, that is carbocations, are electron deficient species. That is why they are unstable. Okay. Now I'm going to write different types of carbocations. Positively charged carbon is directly attached with 3 R groups. So this is tertiary carbocation. Positively charged carbon is attached with 2 R groups and 1 hydrogen atom. So it is secondary carbocation. Positively charged carbon is attached with only 1 R group and rest of the bonds were attached with hydrogen atom. So this is primary carbocation. Positively charged carbon is attached with 3 hydrogen atoms. They are called methyl carbocation. Now we have to understand among these types of carbocations which is more stable. Kana, as I've told you already, carbocations are electron deficient. They don't have electron. That is why they are unstable, right, Kana? Now, as far as tertiary carbocation is concerned, this electron deficient carbon is directly attached with 3 R groups. What is R group? They are basically alkyl groups. What alkyl group will do? See, what alkyl group will do? They are plesyl groups, right? So they are electron donating group. So here all these R groups will push the bonded pair of electrons towards positively charged carbon. Because of this, positively charged carbon will have a moral support, right, Kana? Because we have all the 3 R groups are pushing electrons towards electron deficient carbon, which makes this positively charged carbon relatively stable. As for a secondary carbocation is concerned, we have only 2 R groups for moral support. Here we have only 1 R group. Here we have not even 1 R group is there in methyl carbocation. Now tell me, among these carbocations, which carbocation will be stable? Here carbocations are unstable because of their electron deficiency. As far as tertiary carbocation is concerned, we have 3 R groups to to push the electron towards carbocation. So which will be stable among primary, secondary, tertiary and methyl? Tertiary is more stable because in tertiary we have 3 R groups to push the electron towards carbocation. Because of this, tertiary carbocation will gain more moral support. Here electrons are not getting transferred. Still electrons are being pushed towards positively charged carbocation. Okay. So because of this, tertiary carbocation will be more stable. Then secondary, then primary. Least is methyl. So as this carbocation, free radical were also considered to be electron deficient. So for both carbocation and free radical, this is the stability order. Primary is more stable than secondary. Secondary is more stable than primary. Primary is more stable than methyl. Same thing is applicable for electron deficient free radical also. Now we'll move on to carbanion. Kana, carbanion is unstable because this got extra electron. Okay, so this carbanions are electron rich. So this negatively charged carbon is attached with 3 R groups. So this is tertiary carbanion. Here it is attached with 2 R groups and 1 hydrogen. So it is secondary carbanion. Here carbanion is attached with 1 R group and Rest of the bonds were filled with hydrogen atoms. So this is primary carbanion. A negatively charged carbon is attached with 3 hydrogen atoms. So this is methyl carbanion. So why these carbanions are unstable? Because they have extra electrons. As far as tertiary carbanion is concerned, this carbanion is attached with 3 R groups. And what is the nature of R group? What this R group will do? It will push the electron towards carbanion. See, already carbanion got more electron. That is why it is unstable, right? Now, all the 3 R groups are pushing the electrons towards carbanion. Will it be happy then? Will it be happy, Kana? No, right? Because this carbanion itself is electron rich. That is why it is unstable. Now all the 3 R groups are pushing the electrons towards carbanion, which makes the carbanion even more unstable, right? Now the tertiary carbanion is highly unstable, but relatively methyl carbanion is stable because there is no electron donating group attached directly. Next is primary. This is tertiary. Okay, so this is the stability order, which is very important, which is very, very, very important. Whenever you're studying any chemical reaction mechanism in your 12th standard, understanding the stability of carbocation, carbanion free radical is very important. If you understand this only, you can understand the mechanism also. Okay, fine. Any doubt?
Ma'am, this one last one, how ma'am come first meeting?
Okay, I'll teach you, Mushkin. Kana, carbanion is electron rich. That is why this is unstable. Carbanion, as far as carbanion is concerned, carbanion got more electron. That is why it is unhappy. As far as tertiary carbanion is concerned, this negatively charged carbanion is attached with 3 R groups. What is the nature of R group? They are electron donating groups. Okay, Kana. So what this electron donating group will do? What is its nature?
Push the electron.
It will give electron. Right, Pushkin? Carbanion itself is electron rich. They don't want any electron. But all these 3 R groups will push the electron towards carbanion. Now tell me, will this carbanion will be happy? Already this got so much electron. That is why it is unhappy. Now these 3 R groups are pushing the electrons towards carbanion, which makes this carbanion even more unhappy. You're getting my point, Mishkin?
Okay, ma'am.
That is why it is highly unstable. Here we got only 2 R groups, which is giving electrons towards itself. We have only 2 disturbing groups here. Here we have 1 disturbing group. And in methyl, we have no disturbing group at all. Carbanion is unstable because of its electron-rich nature. But here we don't have extra electron donating groups as far as methyl carbanion is concerned. So it will be relatively happy. You're getting my point, Kana?
Okay, ma'am.
So that is why methyl carbanion is more stable than primary. Primary is more stable than secondary. Secondary is more stable than tertiary. Okay. Now I'll give you a few compounds. Few carbocations, and I want you guys to tell me the proper stability order. This is A, B, C, and D. Could you please tell me decreasing or increasing order of stability of these carbocations. Take your time, find whether that is primary, secondary, or tertiary, and based on the stability order, please arrange these species. Kana.
C first, ma'am. B second. A third. D fourth.
Okay. So, very good. As far as A is concerned, Mushkin, could you please tell me it is primary, secondary, or tertiary?
Ma'am, C methyl group, ma'am.
Okay. Seedana, could you please tell me that order alone? I'll write it here so that we
C
can
first.
check.
C first, ma'am.
Okay. Is it highly stable or unstable?
High stable.
C.
B second, ma'am.
Okay.
A third. D fourth.
So according to you, what I can understand is this D is highly unstable.
No, yes, ma'am.
Unstable.
Yes, ma'am.
Okay. C is most stable. This is your answer, right?
Yes, ma'am.
We'll check. Mushkin, shall we see this question?
Okay, ma'am.
See, what intermediate is there, Kana? Is it carbocation, carbanion, or free radical?
Carbocation.
Okay. Mushkin, it is carbocation, right?
Yes, ma'am.
Okay. What is the stability order of carbocation? I've given you already. What is
Primary,
this?
secondary, tertiary,
See,
methyl.
here I've written the
First tertiary.
yes. So as far as carbocation is concerned, tertiary, secondary, primary, and methyl. Okay. Now we'll see what kind of carbocation is in A. What kind of carbocation is this? Compound A is?
Secondary carbon.
Yes. Here positively charged carbon is attached with two R groups. So it is secondary. This is
Primary.
primary. Here we have no R group.
Methyl group.
So this is methyl. Here this is very good, tertiary. Now we have to know the stability order. Which is most stable?
D.
D. Because that is tertiary. Next,
A.
A. Next, B. Next is C. That's it. This is the proper stability order. Okay, fine. Now I'm going to add one more carbocation to this. Kana, now I want you guys to tell me whether it is primary, secondary, or tertiary.
Tertiary only. ma'am.
Yes, it is tertiary because here also we have three R groups connected to positively charged carbon. Now we have to decide among D and D which is most stable because both are tertiary, right? So whenever both the species are tertiary, whenever both the species are secondary, or when both the species are primary, then using inductive effect we cannot decide which is most stable. So whenever you are getting this kind of confusion, please check for the number of alpha hydrogens. If number of alpha hydrogens are more, then stability is also more. Okay. Now we'll understand what is alpha hydrogen. The carbon which is directly attached with positively charged carbon is called alpha carbon. So these three carbons are alpha carbons, right? Because all the three carbons are directly attached with positively charged carbon. And hydrogens which are attached with alpha carbons are called alpha hydrogen. So could you please tell me how many alpha hydrogens were there in compound D?
3, ma'am.
In one alpha carbon itself, we have 3 alpha hydrogens.
9, ma'am.
Very good. 9 alpha hydrogens. In compound D, we have 9 alpha hydrogens. Right. See the now? Am I right, Kana?
Yes, ma'am.
Yes. In compound D, we have to count number of alpha hydrogens. So, to this positively charged carbon, this is the carbon which is directly attached. So, this is alpha carbon. This is alpha carbon. This is also alpha carbon. This is the carbon which is attached with alpha carbon. So, it is called beta carbon. Now, guys, please count me how many alpha hydrogens are there in compound E.
8, ma'am.
Yes.
Yes, ma'am.
Now, could you please tell me the proper order between A, B, C, D, and E? Which is most stable, which is least stable? Which is most stable and which is least stable? Anyways, most stable is going to be tertiary. Among D and E, which is most stable? The compound with more number of alpha hydrogens are most stable.
D, ma'am.
Very good. After D?
E, ma'am.
Very good. After E?
A, ma'am.
A?
B, C.
That's it, Kana. That's it. So, both are tertiary. This is secondary. This is primary. And this is methyl. If you have confusion between two tertiaries or two secondaries or two primaries, check for the alpha hydrogens. The species with more number of alpha hydrogen will be more stable. This got 9 alpha hydrogens and this got 8 alpha hydrogens. That's it. You're getting my point? Any doubt?
No, ma'am.
Okay. Now, shall we discuss one problem?
Okay, ma'am.
Okay. Yes. Kana, you just tell me the answer. Please take your time. Please read the question, understand the question, and please come up with the option with proper justification.
B option, ma'am.
Come again, Kana. Take your time, understand the problem. So they're asking us to arrange these carbocations in terms of stability.
Ma'am, B option, ma'am.
Second option. Okay. We'll check, Kana. So you have to understand what kind of carbocations were there. So please write that and after which arrange the same. Categorize them as primary, secondary, tertiary, methyl. After which try to arrange it. See, then actually you have to reconsider your answers for me. Mushkan, do you want any clue? If you're working on it, please let me know. I'll give you time. But if you're need of any clue, then please let me know.
Ma'am, first we want to find which is primary, secondary, tertiary.
Yes. Yes, we have to. So, have to do that. As far as compound 1 is concerned, this is my carbocation, right?
Ma'am, they're having first CH3 bracket 2, ma'am.
Ah,
Third one CH2.
So here one side we have CH2, CH3, right?
Yes, ma'am.
Ma'am, first one tertiary, ma'am.
Yes. So here I have CH3 twice, which means I have two CH3 groups. I'm going to write it like this. So this is tertiary. See, Sidra was right. So this is tertiary because positively charged carbon is attached with 3 R groups.
Second one also tertiary, ma'am.
Okay.
I'm seeing previous questions like that only first two, ma'am.
Hmm. So this is also tertiary. How about third one? How about third one? Positively charged carbon is attached with 2 methyl groups and 1 hydrogen. So, Kanna, positively charged carbon is attached with 1 hydrogen and 2 methyl groups. So primary, secondary, or tertiary?
Secondary.
Yes, it is secondary. Fourth one. Positively charged carbon is attached with 2 hydrogens and 1 methyl group. So, yes, it is primary. Here, the fifth one. Positively charged carbon is attached with 3 hydrogen atoms. Now tell me what kind of carbocation is this? We have no R groups there. Yes, it is methyl. So as far as carbocation is concerned, what is the stability order? Tertiary is most stable, then secondary, then okay. So then methyl. So least is methyl. So of course the compound 5 is going to be highly unstable. So definitely option is not second and third. So option A or D. So what is basic order, Kanna? So which is tertiary here? First and second were tertiaries. So if both the systems are tertiaries, what we have to do? We have to check for number of alpha hydrogens, right? So please check for the alpha hydrogens. Which got more alpha hydrogen will be more stable. So as far as the carbocation in the second system concerned, this got 9 alpha hydrogens and this got 8 alpha hydrogen. So this one is highly stable, right? So 2 is most stable. Next is 1. Next is secondary, which is third one, and primary, which is fourth one, and methyl, which is at the fifth one. So this is the right order, which is at the first option. Sorry? Okay. Mushkan, any doubt, Kana?
No, ma'am. After you write this compound, I will understand, ma'am. But
Yes.
how to write? I can't understand, ma'am.
First time we cannot do that, Mushkin. This is the first time we are writing this condensed compound into a normal one, right? I know that if I write it like this, you can understand.
Yes,
Okay,
ma'am.
and first time it is definitely difficult because this is the first time we are seeing the compounds like this. Before this, I didn't teach you like this, right? See, this positively charged carbon is attached with CH3, and this is the CH3 in the bracket, and this is 3 times. So what we have to understand is this positively charged carbon is attached with 3-methyl group. That is what the meaning is. So, since this is the first time, definitely it is difficult for us to convert that into a normal one. So, if we practice this kind of compounds, then it will be very easy. Okay, fine. Seetana, now you have any doubt, Kana?
No, ma'am, I collapsed that option, ma'am, fourth and fifth.
Okay, it happens. It happens. Fine. So today, what are all the stuffs we have discussed? We discussed what is substrate, what is reagent, different types of organic reactions like addition, elimination, substitution reaction, and we know when addition reaction will occur. Substrate has to be double bond or triple bond. That double bond will get converted into single, and triple bond will get converted into double bond. And we understood what is elimination, what is substitution reaction. And under substitution reaction, we had 2 categories like electrophilic and nucleophilic substitution reaction. And after which we discussed reaction mechanisms in which we encountered different types of intermediates like carbocation, carbanion, and free radical upon heterolytic and homolytic cleavage. And we saw when are the scenarios we'll be getting these types of carbocations, carbanions, and free radicals, right? And we saw what is a transition state, and we discussed this inductive effect, and we understood how this inductive effect is helping to understand the stability of carbocation. When both the tertiaries are given, we don't know which is more stable, right? So what I've asked you to do is check for the alpha hydrogen. Checking the alpha hydrogen and deciding the stability is basically hyperconjugation. So hyperconjugation is helping us to find the stability between 2 carbocations. If both are tertiary, then they are asking us to check for number of alpha hydrogens. If more number of alpha hydrogens, then stability is more. Same thing is applicable for 2 secondaries, 2 primaries also. Okay, so basically the key point is it should have a number of alpha hydrogen. So as far as hyperconjugation is concerned, in next class we're going to discuss few more examples under hyperconjugation. Okay, fine. If you have any doubt, please let me know. We'll discuss. Else we'll close the session.
No, ma'am.
Okay. How about Seedana?
What, ma'am?
Okay. Okay, Kana. Fine. Fine,
Thank you
Mushkin.
so much for your good teaching, ma'am.
It's my pleasure. Okay. Bye, Kana. Bye, Mushkin. Bye, Seedana. Bye. Good night.
Thank you, ma'am.
Sir? Sir?